For those of you that are doing A-level maths, and maybe even those watching this video who happen to be doing GCSE maths as well, you've probably come across problems in your textbooks and on past papers and in the classroom that require you to express your answer in an exact form, or require you to give the exact value of the area of such and such a shape, for example. Why is this? I'll try to give some of the reasons, of course from my own perspective, why this might actually be. I don't know how successful I'm going to be with this. I've jotted down a few ideas, some things that I want to mention. Whether I'm successful, whether I give an adequate explanation is entirely up to you to decide. If not, then at least I hope that I provoke a bit more further discussion on this. Unfortunately, many A-level math students never really get their heads around the concept of exact value in a mathematical context. They interpret the word exact in a way that's maybe appropriate for everyday use, or even for use in a scientific context, but which is not appropriate for a mathematical context. For example, if someone asks us the time, sometimes we might reply by saying, it's exactly 11 o'clock. And of course, when we say exactly here, it's not meant in a literal sense. In reality, it may be a few seconds before or after 11 o'clock. But anyway, no matter how accurately we're able to measure time, we could never say it is exactly 11 o'clock and mean it literally. Will always be some amount of time either side of 11 o'clock. Even in a scientific context where things such as masses, electrical currents and temperatures can be measured to a very high degree of accuracy with cutting-edge technology, we're never able to say that the current through an electrical circuit is exactly 1 amp. It will in reality be either slightly more or slightly less, and may even imperceptibly change over time. However, an imperceptible change is still a change. Mathematics, however, is not interested in measuring the things of the world. Mathematics does not use things to measure with, things which are subject to real-world limitations. And mathematics is not science. Mathematics is its own thing. It has its own methods. It has its own techniques. Mathematics deals with abstract objects and structures which are created by the human mind, and mathematics explores the relationships that exist within and between these abstract objects and structures. And it was a discovery of the ancient Greeks who realized that we don't need to physically measure things to compare them. Indeed, we can't physically measure ideal objects. Nevertheless, we can still compare ideal objects through rational investigation. Mathematics demands an infinite level of precision and accuracy. Nothing less will suffice. And mathematicians have realized that by insisting on this infinite level of precision and accuracy, that the limits of the human mind and imagination can be better explored. When we deal with exactness, ideas are sharp and well defined, not fuzzy or hazy or ambiguous. The logic that was developed by the aforementioned ancient Greeks demanded that either two things be equal or unequal. Thus, two lines either have equal lengths or they have unequal lengths. It is either one or the other, not neither and not both, and not possibly one or possibly the other. Two numbers are either equal or unequal, not both, not neither, and not possibly one or the other. There's no kind of equal. This is the logic that classical mathematics is typically based on. And of course, the exactness that mathematicians demand is not appropriate necessarily for measuring the real world, whatever we mean by real world, in which the boundaries between objects may not be so clear. So I'm not exactly going to belittle science for not following the example of mathematics, because science and mathematics work in completely different ways and have completely different aims. Mainstream mathematics education in the UK does not emphasise anywhere near enough the requirement for exactness in mathematics. Sadly, Mathematics is treated as a mere tool for engineers and scientists, and so much of the current content of a typical A-level maths course has loads of real-life questions shoved into the mathematics textbooks to make mathematics relevant, in inverted commas, which I personally find utterly offensive. And so because of this, A-level maths students often come to view mathematics as working in the same kind of experimental way that science does. And because of this influence, there's still a tendency for GCSE and A-level maths students to think that exact number is one just written to a large number of decimal places, because that would suffice in a scientific context. Large number of decimal places often meaning about 10, around the length of a typical calculator display. And I'll often have to explain to my students that this is not what is meant by exact. It doesn't matter how many decimal digits of, say, the square root of 2 you write out. It will never be the exact value of the square root of 2. But if we are to drop the idea of exactness, how close should a number be to another number for them to be considered the same? How close to 2 does a number have to be considered equal to 2? Agreement to 20 decimal places? 100? 1,000? But even if we choose agreement to 1,000,000 decimal places, why do we choose that? Is there any logical difference between agreement to 1,000,000 decimal places or 1,000,001 decimal places? Any cutoff point is not motivated by logic, but is purely arbitrary. And here we get into disagreements from different individuals and different groups who would demand and expect different levels of accuracy. And so when I talk about the number 2, I might be talking about a certain set of numbers. And when you talk about the number 2, you might be talking about a different set of numbers. So how then can we know what we mean by the number 2? How can we determine the properties of the number 2 if we don't really even know what it is? Will the 2 that I talk about today be the same 2 that I talk about tomorrow? Maybe next week I'll require a different degree of accuracy. Who knows? And so to avoid these sorts of ambiguities, exactness in a very literal sense is a core concept within mathematics. Rounded values, approximate values, and so on have no place in mathematics. And when I talk about mathematics, I mean pure mathematics. You're not doing mathematics when you work with approximate values. Either you're talking about a particular definite number, or you are not. If mathematicians rejected the notion of exactness and demanded only a sufficiently high degree of accuracy, possibly to a certain number of decimal places, then things like differential and integral calculus would have no use, may not even exist. What would motivate us to develop exact techniques for integration when we could just approximate areas to a high degree of accuracy using rectangles? By demanding exactness, we take things to an entirely new level where we stretch our rational minds to its limits. And if we can achieve that level of precision and accuracy, then why should we settle for less? Humans have an incredible gift which allows us to think abstractly, logically, and rationally. It's our duty to explore the limitations of this gift. Mathematicians don't demand exactness because it's easy, but because it's bloody hard.